All right, so basically our claim is that the two linearly independent solutions that we are looking for is this solution here, and the other one was, as we mentioned earlier, C1 e to power lambda t. So the two linearly independent solutions, in this case are C e to power lambda, C1 e to power lambda t, and this solution here, C1t e to power lambda t plus d e to power lambda t, with d as defined above. Now, how can we show that these two solutions are linearly independent? So proof of linear independence. First, I want to show that C1 and D are linearly independent. First, we show that C1 and D are linearly independent. What happens if they are not linearly independent? If not, then we can say that C1 is equal to, let's say, beta D for some constant beta. If two vectors are not linearly independent, then one of them can be written as a scalar multiple of the other one. This is a simple fact from linear algebra. Then what can we say about, so remember, A minus lambda I times D has to be equal to C1, has to be equal to C1. So let me write, I can write C1 as a scalar multiple of D, or D as a scalar multiple of C1, doesn't matter. Let me write it the other way around. So let me write D as, let's say, some constant beta times C1. Doesn't matter. We can write each of them as a scalar multiple of the other one. If D is beta C1, then C1 will be 1 over beta D. So please note that everything is non-zero here. C1 is non-zero, D is non-zero, therefore beta is non-zero. And we can divide by beta as well. So D, let's say, is equal to beta C1. Now, what can I say about A minus lambda I times D? Then A minus lambda I times D will be equal to A minus lambda I times beta C1. D is same as beta C1, and then I can take beta as a constant, take it out. So beta times A minus lambda I times C1. And what can I say about A minus lambda I times C1? Well, C1 is an eigenvector with eigenvalue lambda. So that means AC1 is same as lambda C1, or in other words, A minus lambda I times C1 must be 0. So this is same as beta times 0, which is 0. Remember, AC1 is same as lambda C1. So A minus lambda I times C1 will be 0. So, but remember, A minus lambda I times D was supposed to be equal to C1. Now I got A minus lambda I times D equals 0. So this contradiction with A minus lambda I times D equals C1. Because remember, C1 is non-zero. Every eigenvector is non-zero. So A minus lambda I times D must be C1, and C1 is non-zero. So A minus lambda I times D must be non-zero. But we just saw that if C1 and D are linearly, if C1 and D are not linearly independent, then A minus lambda I times D will be zero, but it must be non-zero. So what does that mean? So this implies that C1 and D are linearly independent. Because we saw that if they are not linearly independent, then we will have a contradiction. Now that we've showed C1 and D are linearly independent, we can show that the solutions that we had here, these two solutions, are linearly independent as well. So next we will show that, we show that the solutions above, which are C1 e to power lambda t and C1 times t e to power lambda t plus d e to power lambda t are linearly independent. So how can I show that two solutions are linearly independent? I have to assume that some linear combination is zero. Let's say alpha 1 times first solution plus alpha 2 times second solution is zero. And then I have to show that alpha 1 and alpha 2 are zero. So let's say alpha 1 times C1 e to power lambda t plus alpha 2 times C1 t e to power lambda t plus d e to power lambda t equals 0. So this is supposed to be true for every t. So it will be valid for t equals 0 as well. So if I replace t with 0, then I'll have alpha 1 c1 plus alpha 2 d equals 0. If you replace t with 0 here, this will vanish. And then you'll be left with this term because e to the power 0 is 1. So alpha 1 c1 plus alpha 2 d will be 0. And now here C1 and C2 are linearly independent. We just showed a few minutes ago. C1 and C2 are linearly independent. So therefore, if alpha 1 C plus alpha 2 D is 0, then both alpha 1 and alpha 2 must be 0. This is definition of linear independence, that if some linear combination is 0, then every coefficient must be 0. So here C1 and D linearly independent. Which is what we proved above, C above. So that means alpha 1 must be equal to alpha 2 must be equal to 0. And once I show alpha 1 and alpha 2 are 0, that means the solutions that I wanted to show they are linearly independent are proved to be linearly independent. So the solutions C1 e to power lambda t and C1 t e to power lambda t plus d e to power lambda t are linearly independent. Are linearly independent as desired. We wanted to show that they are linearly independent. And we showed that some linear combination, if some linear combination is 0, then every coefficient must be 0. That means they are linearly independent. Now this vector D that we have here in the solution, the second solution appeared in the second solution, is called a generalized eigenvector for our matrix. So let me mention this as a remark. The vector D which, if you remember, was obtained via A minus lambda I times D equals C1, is called an eigen. It's called a generalized eigenvector. Generalized eigenvector for A with eigenvalue lambda. Why is it called generalized eigenvector? Well, we know that A minus lambda I times an eigenvector is 0. Now this is A minus lambda I times this D is C1. But what about if I, instead of A minus lambda I, what about if I consider A minus lambda I the whole square? So the reason for this name, see, if C1 is an eigenvector, then we can say that A minus lambda I times C1 is 0. Now if D is generalized eigenvector, what can I say? So then I can say A minus lambda I squared times D will be same as A minus lambda I times A minus lambda I D. But A minus lambda I D, I know it's C1. See here, A minus lambda I times D is C1. So I can replace this with C1. So then I'll have A minus lambda I times C1. And I already know that A minus lambda I times C1 is 0. So A minus lambda I times C1, this will be 0. So instead of A minus lambda I times the eigenvector equals 0, this time we have A minus lambda I raised to some power times generalized eigenvector equals 0. So for this reason, because this power 1 is replaced with some other power, so this vector is called a generalized eigenvector. Now, before moving on and doing an example, let me also mention about the phase portrait. We can mention this also as a remark. Now, in the case of repeated eigenvalue and the phase portrait, looks as one of the following forms. So again, this time we have two possibilities for the phase portrait. All right, so the phase portrait would look like either like this or like this. So in each case, please note that we have one eigenvector. So repeated eigenvalues, I mean with one eigenvector, one linearly independent eigenvector. Because we say we have two linearly independent eigenvectors, then we have just that happens only in the case of diagonal matrix with same diagonal elements, and we already considered and solved it before. Right now we are considering the case where we have repeated eigenvalue with one eigenvector. Maybe I can emphasize here with repeated eigenvalue with one linearly independent eigenvector a phase portrait looks as one of the following forms. So either looks like this or like this. So in each case, as you can see, there is one eigenvector. There is only one straight line. You know, if the initial condition lies on one of and the direction of the eigenvector, we saw before that we will stay on the same line. But other than that, if the initial condition x of 0 starts from anywhere else, we won't stay on a straight line. We will be on a curve. And right now we have only one linearly independent eigenvector, so only one direction. So along this direction or along in this direction, in this case, we will stay there. If the initial condition starts from here, for example, we will stay in the same line and the same line. Or in this case, if we start from somewhere here, we will stay on the same line. Now the question is, well, we'll stay on the same line, but do we go towards origin or do we get farther and farther from origin? Well, if eigenvalue is positive, then we know that the solution looks like, you know, C1 e to power lambda t. If lambda is positive, as t goes to infinity, e to power infinity will be infinity. So in that case, we'll get farther and farther from origin. But let's say if we have C1 e to power lambda t with lambda negative, as t goes to infinity, we'll have e to power minus infinity, which goes to 0, which is the case here. So this will be valid if lambda is negative, and this will be valid if lambda is positive. Now, let's look at an example. We saw about how to find the solution, and we saw the phase portrait. So now we can do, consider an example here. Example, find the general solution of x prime equals 7, 1 minus 4, 3 times x, and sketch the phase portrait. The phase portrait for this system of ODE. So first we need to find the eigenvalues, like always. You know, here A is 7, 1 minus 4, 3. So first, find the eigenvalues. So how do I find the eigenvalues? I need to solve for determinant a minus lambda I equals 0. So that gives me determinant 7 minus lambda, 1 minus 4, 3 minus lambda equals 0. So that gives me lambda minus 3 times lambda minus 7 plus 4 plus 4 equals 0. So that gives me lambda squared minus 10 lambda plus 21 plus 4 equals 0. So that gives me lambda squared minus 10 lambda plus 25 equals 0. And that gives me lambda minus 5 the whole squared equals 0. So I will have here two eigenvalues, but both of them are the same number, 5 and 5. So lambda 1 equals lambda 2 equals 5. Repeated eigenvalue. Repeated eigenvalue. Now we need to find the eigenvector. So please note here that here the matrix is not a diagonal matrix. Now, diagonal matrix means these elements must be 0. So because it's not a diagonal matrix, we won't have two eigenvectors, two linearly independent eigenvectors. We will have only one linearly independent eigenvector. So if you remember, we previously considered two cases. One case, two linearly independent eigenvectors, which happens only if your matrix is diagonal, and the other case was having a one linearly independent eigenvector. So here we have only one linearly independent eigenvector. How can I find it? We need to solve, a minus lambda I times, let's say, c equals 0. This is vector c. So that means a minus lambda. Lambda is 5. So 7 minus 5 is 2. 2, 1. And minus 4. 3 minus 5 minus 2. Let's say x1, x2 equals 0. So that gives me 2x1 plus x2 equals 0. And minus 4x1 minus 4x1 minus 2x2 equals 0. So as you can see, this equation is repetition of this equation. You only need to multiply both sides of this equation by minus 2. And then we get this equation. And we saw before that in this type of question, the other equation is a repetition of the first one. Sometimes obvious, like this example, sometimes not obvious. So here I can consider only one of the equation. Let's say the first one, and then I can find x2 in terms of x1. x2 is minus 2x1. Now if I set x1 to be, let's say, 1, so let's say set x1 to be 1, then x2 will be how much? x2 will be minus 2. So the eigenvector c1 will be 1 and minus 2. So let me first sketch the phase portrait. And then we can solve the system, find the solution. So 1 and minus 2, 1 and minus 2 looks like this. So this will be the direction of the eigenvector. Direction of the eigenvector. And then do we go towards origin or do we get farther and farther from origin? Well, here lambda was positive, was 5, which is positive. So lambda equals 5 is positive. So that means we get farther and farther from origin. And for the rest of the phase portrait, because this part of phase portrait we can figure out by analyzing the situation, and the rest of it we can use the references, phase portrait references that we had. We had 2 of them, and in the case that we get farther and farther from origin, we know that the rest of graph looks like this. So we just need to use this one to complete our phase portrait here. So here is how we completed the graph. So I can say figure, I can call this, let's say case, let's say figure, say 3. I think we had 3 before, so let me call it figure 4. And this one figure 5. So we use figure 4 above. To complete the phase portrait. So this part of the phase portrait, we can analyze it based on like the property of eigenvalue, eigenvectors, and the exponent, which is positive, so the solution gets farther and farther from origin. But to complete the rest of the graph, you can use a software, or in this case, use the references, the reference figures that we have. So here, figure 4, I called this one figure 4. I think my screen was freeze for a few seconds, but I called this figure 4, this one figure 5, this one positive eigenvalue, this one negative eigenvalue. Here we have positive eigenvalue where we get farther and farther from origin along the eigenvector. And then, we said that we use figure 4 above to sketch the phase portrait in this case. And here lambda is 5, which is a positive number. Now, this is a phase portrait. What about finding the solutions? So finding the solutions. Finding the solutions. So what were the solutions? For solutions, if you remember, we needed C1 and lambda, which we already found. We also need D, the generalized eigenvector. So we need to find D, generalized eigenvector. How do I find the generalized eigenvector? A minus lambda I times D should give me C1. C1 in our case is 1 and minus 2. And so that means A minus lambda I, we already saw it here, it's 2, 1. This matrix here is A minus lambda I. 2, 1 minus 4 minus 2. 2, 1 minus 4 minus 2 times D. Let me call it, for example, let's say T1, T2, I can call it T1, T2. Or let me call X1, X2 again, doesn't matter. Let's say X1, X2 equals 1 and minus 2. So then that means 2x1 plus x2 equals 1 minus 4x1 minus 2x2 equals minus 2. Again, as you can see, the second equation is the repetition. A repetition of the first equation. First equation above. When you look at the second equation, it's simply the first equation, which is multiplied by minus 2. If you multiply the left-hand side and right side of the first equation by minus 2, then you will get the second equation. So I only need to consider one of them again. So I can consider the first one. First one gives me x2 equals 1 minus 2x1. So now I can set, let's say, x1 to be 0. And then x2 will be 1. So I can set D to be 1. I can set D to be 0 and 1. So once I have D and I already have C1 and lambda, I can find the two linearly independent solutions. So hence, our two linearly independent solutions will be C1 e to power lambda t and C1 t e to power lambda t plus d e to power lambda t, which is going to be, we have everything here. C1 was 1 and minus 2. So 1 and minus 2 e to power 5t and 1 and minus 2 t e to power 5t plus d, which is 0 and 1 e to power 5t. So these are the two linearly independent solutions. And then the general solution will be a linear combination of linearly independent solutions, like beta 1 times the first solution plus beta 2 times the second solution. So I can say beta 1 times 1 and minus 2 e to power 5t plus, let's say, some beta 2 times the second solution, which is 1 and minus 2 t e to power 5t plus 0 and 1 e to power 5t. This will be the general solution, and beta 1, beta 2 here are constants. All right, guys. So far, all cases that we considered were homogeneous systems. The systems in the form, let's say, x prime equals ax. So far, we solved systems of the form x prime equals ax. Homogeneous systems. Now, let's consider a system of the form let's say x prime equals ax plus g of t for some non-zero vector g of t, for some g of t not equal to 0. If g of t was 0, then we would be back to x prime equals ax, which we already considered it. Now, the solution of this non-homogeneous system, so this is called a non-homogeneous system. So similar to before, we can say that the general solution of the system above can be written as, so how do you write the general solution of a non-homogeneous equation in that case? We said x or yc plus yp, where yc was a complementary solution, the solution for homogeneous system, and yp was one particular solution for the non-homogeneous equation. So we have a similar situation here. The solution, general solution x, can be written as xc plus xp, where xc is the general solution of x prime equals ax, the homogeneous system, and xp, a particular solution. A particular solution. Now again, how do we find, we already know how to find xc. Now the question is, how do we find xp? So again, to find xp, we have similar methods that we can use the similar methods that we used before, which were undetermined coefficients and variation of parameters. So again, similar to before, xp can be found using undetermined coefficients method or variation of parameters. Method. So let's look at an example. Let's say if we have x prime equals, let's say find the general solution of x prime equals 1, 2, 3, 2, x plus 2t and minus 4t. So again, we have x prime equals ax, and this is my g of t. So we need to find xc, the solution for a homogeneous equation x prime equals ax, and xp, a particular solution. So first, let's find xc. For xc, I need to consider x prime equals ax, and which is going to be like 1, 2, 3, 2 times x. How do I solve this? First, I need the eigenvalues. We need eigenvalues, eigenvectors. So I need to solve for determinant a minus lambda I equals 0. That gives me determinant 1 minus lambda, 2, 3, 2 minus lambda equals 0. That will give me lambda minus 2 times lambda minus 1 minus 6 equals 0. So lambda squared minus 3 lambda plus 2 minus 6, that's minus 4 equals 0. So lambda minus 4 times lambda plus 1 equals 0. So I will have two eigenvalues, lambda 1 equals 4, lambda 2 equals minus 1. Then I need to find two eigenvectors, one corresponding to lambda 1 equals 4 and one corresponding to lambda 2 equals minus 1. So check that eigenvector corresponding to this will be C1 equals 2 and 3. And the one corresponding to this will be C2 equals minus 1 and 1. So xc of t, can be written as follows. So some linear combination of C1 e to power lambda 1t and C2 e to power lambda 2t. So I can say alpha 1 C1 e to power lambda 1t plus alpha 2 C2 e to power lambda 2t, which is going to be same as if I substitute, then I'll have alpha 1 times 2 and 3 e to power 4t plus, let's say, some alpha 2 C2, which is minus 1 and 1 e to power minus t. for some constants alpha 1 and alpha 2. So this is my xc, which we already explained about this before. Now for xp, the non-homogeneous part, we can use the undetermined coefficient, so we can guess basically the general form of xp. So for xp of t, so let's guess a particular solution to be of the form, let's say some a1t xp of t equals, let's say a1t plus b1 and a2t plus b2. Remember from before when we had just one equation, let's say if the non-homogeneous part was, let's say 2t, we would have the guess for particular solution to be at plus b. If it was, for example, t squared quadratic, then our guess would be at squared plus bt plus c. Now here, the non-homogeneous part is 2t, so our guess will be like a1t plus b1 for the first coordinate. The only difference is that this time we have two coordinates, but we have a similar argument for each of the coordinates. For the first coordinate is 2t, so our guess is like at plus b. And second coordinate, it's written as minus 4t, so my guess will be like ct plus d. So you can write at plus b and ct plus d for the second coordinate, or you can write like a1t plus b1 and a2t plus b2. So you can name the coefficients the way you the way that you are more comfortable with. We can name them as like a, b, c, and d, like at plus b, ct plus d, or we can name them as a1t plus b1 and a2t plus b2. So this is my xp of t. Now what will be derivative of this? So xp prime of t will be a1, a2. Just derivative of a1t plus b1 is a1. Derivative of a2t plus b2 is a2. Now what do we need? We need xp prime to be axp plus g of t. I want xp to be a solution of this, right? So I need xp prime to be ax plus g of t. So that means a1, a2 must be same as matrix A. This matrix A is 1, 2, 3, 2. Remember, I am solving for x prime equals ax plus g. xp is a particular solution. So for xp, we need to have xp prime equals axp plus g. So xp prime I already calculated. Now I need to find axp and then add it with g of t. A is this matrix 1, 2, 3, 2. So 1, 2, 3, 2 times xp, which is a1t plus b1 and a2t plus b2, and then plus g of t. G of t will be 2t and minus 4t. So if you expand the right-hand side, you will have a1t plus b1 plus 2a2t plus 2b2 plus 2t. And then second coordinate will be 3a1t plus 3b1, 2a2t plus 2b2, and minus 4t. And if I rearrange the terms, I can write this one as t times a1 plus 2a2 plus 2. There are three terms that contain t in the first coordinate, and then two terms that do not have t, plus b1 plus 2b2. And then similarly here, 3t times 3a1 plus 2a2 minus 4 plus 3b1 plus 2b2. And this is supposed to be same as a1, a2. So I will have a1 equals t times a1 plus 2a2 plus 2 plus 2 plus b1 plus 2b2, and also a2 will be same as t times 3a1 plus 2a2 minus 4 plus 3b1 plus 2b2. Now if I compare coefficients of powers of t in left hand side and in right hand side, then I can say that coefficient of t in the right hand side, the first equation is a1 plus 2a2 plus 2, so that has to be 0. Coefficient of t, see in the right hand side I have some t term, and left hand side I don't have any t term. It's just, this is just a constant. Similarly, this one I have a t term in the right hand side, left hand side I don't have a t term, so this has to be 0 as well. So 3a1 plus 2a2 minus 4 has to be 0. So from these two I can find the a1 and a2. So this will give me a1 equals 3, a2 equals minus 5 over 2. So this is for powers of t. Coefficient of powers of t in left hand side and right hand side. Similarly now, coefficients of powers of t to power 0, which means constant terms in left hand side and right hand side. Now if I compare the constant terms in left hand side and right hand side, for the first equation the constant term left hand side is a1, right hand side is b1 plus 2b2. So a1 was b1 plus 2b2, and for second equation a2 will be same as 3b1 plus 2b2. But we already know the values of a1 and a2. a1 was 3, and a2 was minus 5 over 2. And these two equations will give me the value of b1 and b2. b1 will be equal to minus 11 over 4. b2 will be equal to 23 over 8. So then the particular solution will be xp of t was, if you remember, a1t plus b1, a2t plus b2. So that will be 3t minus 11 over 4 and minus 5 over 2t plus 23 over 8. So this is xp. And lastly, the general solution can be written as x equals xc plus xp. And we already found xc and xp. xc was alpha 1 minus 1 and 1 e to power minus t plus alpha 2, 2 and 3 e to power 4t. And xp, we just found it above, 3t minus 11 over 8 and minus 5t over 2 plus 23 over 8. So this is the general solution for our equation. A solution for non-homogeneous system. Okay, guys, that's all for today. Thank you and see you next time.